Okay, now let's continue with chapter 1. So last time we talked about semiconductor physics, and now we talk about semiconductor devices. So what device do you know? So what semiconductor devices do you have learned? So we have PN junction, right? And we also have like a transistor. For the transistor, there are two types of the transistors. One is called the MOSFET, metal oxide semiconductor field effect transistor. So the other one is called bipolar transistor. So now we will look briefly at the PN junction and the two types of the transistors. The first one is the PN junction. So what's the use? Of the PN junction? So we know about like so solar cell. The solar cell use PN junction. Another one is the light emitting diode. So we have the photo detectors. So photo detectors is also based on the PN junction. And we also have the rectifier. Do we have anything else? So we have laser diode. So they are all based on the PN junction. So PN junction, so you can see we have N semiconductor and the P semiconductor. This is the P, this is N. If we bring them together, so this is why we have a lot of holes. This is why we have a lot of electrons. But when they come together, you can see so electrons will move to the left and hole will move to the right. So in the end, so we have this something called a depletion region. And that means there is no free carriers. There is no free carriers in this region. So actually, there is free carriers because usually we have this Pn equals Ni squared. So we have this formula here. So the Ni is very small. So here there's still some P and some N, but the number of the P and N is very, very small. This is called a depletion region. So actually, when you bring two materials together, there is always such kind of charge transfer. For example, if you have a piece of like aluminum and a piece of gold, if you put them together, there will also be some charge transfer. So luckily, for example, electron from the gold will come to the electron of the aluminum if they have different work function. So if the two material they have different work function, then when you bring them together, there will be charge transfer. So here is the same thing. The work function at the Fermi level of the P and N will not be the same. Then when you bring them together, there will be charge transfer, right? We have charge transfer to form this so-called depletion region. So we have this depletion region. So here is positive charge, and here we have negative charge. So we have this electrical field. So we have this field. So this field will block further diffusion of the electron to this side and hole to this side. So in the end, there will be no barriers. There will be in equilibrium. There will be no current, because we have the diffusion current from electron from here, hole from here. So this is called the diffusion current. So the diffusion current will balance the drift current. The drift current is caused by the built-in electrical field. The drift current is given by something like this. So this is the drift current. It's based on the built-in electrical field. So the drift current and the diffusion current, the drift and diffusion, they will cancel off each other. There is no current. So when we have this forward bias, so the electrical field will be something like this. So this is the forward bias. Now this forward bias, you can see the field direction will be to the right side. So the field in the junction will be to the right side. So the field from this bias will cancel out the field of this built-in field. As a result, the depletion layer will be narrower and the field will be smaller. So we have this electron can come from the right to the left and hole come from the left to the right. So we have this is called a forward bias. So we have very large current. We have the large current. So when we have the reverse bias, So for the reverse barriers, so the depletion region here, the depletion region will be widened, but only very small leakage current will flow. So in the end, we get this formula: I equal to I0 E QV, electron charge, voltage, KT minus 1. So this is the basic idea of the p-n junction. So now let's look at transistors. So the first type of transistor is the MOS transistor. MOS means metal oxide semiconductor. So MOSFET is metal oxide semiconductor field effect transistors. So now let's look at how MOSFET works. So here we have this MOS, that means the metal here, the metal oxide semiconductor. So this is if we look at this way, so we have the MOS, metal top oxide in the middle, semiconductor at the bottom. So we have the source and the drain. So this part is called the channel. So source, channel, drain. So something like this. So this will function like a switch. This is the source, this is the drain, and we have the control. So this control is the gate. So when we have negative gate voltage here, so the hole will be attracted to this region. Now this part become a lot of holes. So if we look at the current from here to here, so you can see that. So here is the positive barriers, here is the grounded. So this junction here is reverse barriers, right? So this junction here, the P to N, this one reverse barriers. So this one NP, this is forward barriers. Because this one is reverse barriers, the most of the voltage, most of the VD will fall on across this junction. But because we know the reverse barriers is like broken, the current cannot flow. So in this case, no current flow from the source to the drain. The same is true for the depletion region. In this case, we apply positive voltage. So this positive voltage will push away the holes. The hole will be pushed away. But still, this side is like a N-type, no carrier. This is like a P-type, Then this one is reverse barriers, so currents cannot flow from here to here because this junction, P-N junction here, is reverse barriers. This is still off, so it is still an off state. So when we have very high positive barriers, then we have this inversion. The inversion means this one is the P-type, but because of the very large positive barriers, there will be a very thin layer, like 5 nanometer thick layer on the top surface. It is inverted. That means there is a lot of free electrons in this area, free electrons in the top 5 nanometer. As a result, so electrons come from here to the top 5 nanometer, come to the drain. So we have the current flow from the source to the drain. So this is what we see the transistor is on. So this is how the MOSFET works. Effectively, for the digital circuit, it is like a switch. So the gate control the current flow from the source to the drain. So now let's look at another transistor called the bipolar junction transistor. So if we look at this figure, so we have this N minus substrate. Then we have this P-type. The P is the control. This is the base. N minus is the collector. So N minus here is the collector. But here we have this N plus. This N plus is to reduce the contact resistance. So when we have this heavily doped, the contact between the metal and the semiconductor, the contact resistance will be low. It's called contact resistance. So this here, this doping here, heavy doping is to reduce the contact resistance. But then we have this is the emitter. So in the operation, so we have here the grounded, emitter is grounded, base is small positive barriers. The base is small positive barriers to the base, and we have large positive barriers on the collector. If we look at here, if we look at this figure here, you can see from emitter to the base, we have the positive barriers here. Now this one is forward barriers. So there will be current flow from here to here. There will be current flow from emitter to the base, because this is the forward forward barriers. So this one is a bigger positive voltage. So this is higher voltage than the base. We can see here, from here to here, this one is reverse barriers. So there will be, so normally there will be no current flow from here to here, because this one is reverse barriers. So you can see, for the reverse barriers, this graded area, the graded area here, this is the depletion region. So this depletion region, the gray area depletion region is very wide for the reverse barriers. For the forward barriers, the depletion region is small. So you normally can think there will be no current flow. There will be no current flow from here to here, because this one is reverse barriers. But actually, this is not the case for the bipolar junction transistor, because the base here is very narrow. That means this is very narrow. It is very different from, it's totally different from two independent pin junctions connected through the base region. So we cannot consider this transistor as two pin junctions, one here, connected by the base. But we have to consider that the base here is very narrow. If we look at this figure, you can see that when we have this positive barriers, there will be a lot of electrons come from here to here. So normally you may think that electron will come from here to go to the base, but actually, because this is very narrow, so electron diffuse from here, then it will keep going to the right. It will be collected. So that means electron come from here to here, and because this is very narrow, it keeps moving forward. Once it gets into this depletion region, so here you can see we know the electrical field. So in this depletion region, we have very high electrical field that's point this way. So that means once the electron come into this region, it will be accelerated and it will go to the collector. So effectively, we can use the base voltage to control the current flow from here to from the emitter to the collector. So it is like this. You can see we have the base to control the current flow from emitter to the collector. So the base control current flow from emitter to the collector. So it is also a kind of a transistor. It is also a kind of a switch. So this is why you can see all the region here, all the junctions, this junction here and this junction here. You see all the junctions that are below the silicon surface. So the device will not be sensitive to the contamination on the surface. If we have some junk on the surface, this is not a problem because the junction is below the surface. But for the MOSFET, you can see if you have some contamination here, if we have some contamination between the oxide and silicon surface, then the performance will be bad. That is why in the 1960s, so people use bipolar junction transistor for the logic circuit rather than MOSFET, because for the MOSFET, we have this stability problem of the silicon and silicon oxide interface. So here we see again, in the 1960s, at the beginning, as we said, we used bipolar junction transistor. So this is the NPN. We have the resistor. We can form this logic circuit. So the doping is done by the gas phase diffusion for the doping. The N minus, this layer is by the epitaxial growth. So we will learn about epitaxial growth later on. So here we have this P plus here, and P plus here, N plus here. So those actual doping is for the device isolation. That means this transistor will not crosstalk with the other devices nearby. So this is for the isolation between the different components. In the 1970s, we have something called ED NMOS. So why NMOS? NMOS is the electron. We have electron come from here to here. So we know that electron has the mobility 3 times that of the whole mobility. So this way, when we use the NMOS, the speed will be faster. So what is E and D? So E means enhancement. This is the regular MOSFET. So that means so the device is off at the 0 gate voltage. So normally you can see it is off. We have reverse junction here, reverse P junction here. So on the right side, it's called a D. D means a depletion mode NMOS. That means the device is on and 0 gets bias. So when there are no bias, it is on because electron come from here. This is N. This is also N. This is also N. The electron can come from here, so here. So we have the current flow when there is no bias. But this one can be turned off. So when you have negative voltage, and you push away electrons, then this part becomes depleted. Then it is off. That means it can also be turned on and off. But normally it is on. It is on without a bias. In the 1980s, we have this something called a CMOS, complementary MOSFET. That complementary means the number of NMOS and the PMOS is the same. Every PMOS comes with the NMOS. So the main advantage is the lower power consumption. For example, this one is the inverter. This logic circuit is the inverter. Inverter means well, one is the input, then the output will be 0. If the input is 0, the output will be 1. So this is the invert from 1 to 0, from 0 to 1. For example, if this is 1 means high voltage. So when we have a high voltage, this one is turned off, large resistance, and this one is turned on, low resistance. So the output is connected to the ground. So we have 0. So when we have 0, low input, low voltage, or negative voltage, this one is on, this one is off. So we have the output is connected to plus voltage, so it's high voltage, it is 1. So there is no power consumption because this PMOS and this NMOS, only one of them will be on, the other is off. That means there will be no current flow from here to here. But if you look at this one is you have the N, like kind of NMOS, and you have the transistor here. So you have the resistor. So that means the one of either this one or this one will be replaced by the resistor. Then if this one is on, there will be current flow from top to the bottom. So we have the power consumption. That way, the CMOS, the main advantage is low power consumption. In the 1990s, so we have this called a BiCMOS, a bipolar junction transistor and the CMOS, they come together. Now this one, bipolar junction transistor, is used for the driving circuit. Now this CMOS is used for the logic circuit. Okay, so far we have finished the background knowledge. So we have talked about semiconductor physics and semiconductor devices. But now we will go to the microfabrication part. So this is the we go to the microfabrication. That is the focus of this course. So this is about chip fabrication. This is the technology used to manufacture the integrated circuit. But the same technology can also be used for other applications. For example, the same technology can be used for the large area display, hard disk drive, lasers, MEMS, micro electromechanical system, lab on a chip, like this for the biomedical device, and solar cell. As a result, this is what you learn here will be used for many different things. For the nanofabrication, what you learn here is also the basic. The main difference, nanofabrication and microfabrication, is that for the nanofabrication, we use electron beam lithography and focused ion beam and other lithographies. But for microfabrication, we mainly use photolithography. But the other technique, like the thin film deposition and thin film etching, is the same. Therefore, as I said here, what you learn here will not only use for the IC manufacturing, it will also be used for many other fields. So here I give you a simple example of the fabrication process. So we want to make this a MOSFET. So we have the source, drain, gate, metal electrode. This is isolation, for the isolation. So how to make this? How to make the MOSFET? Well, there are 3 components for the macro and nano fabrication. So the first one is the lithography. So lithography is the generates the pattern in a material called resist. For example, how wide of this line? This gives you the channel length. So the channel length from here is determined by the lithography step. Then we have the thin film deposition. The thin film deposition is an additive process. For example, the red color here, the red color material, in the past, this is the polysilicon. The polysilicon is deposited by the chemical vapor deposition. This is the thin film deposition process. Then we have the etching, which is the subtractive process. For instance, we'll deposit this red color polysilicon, and it will be coated everywhere. You have the silicon everywhere. How to remove the red color polysilicon here, from here and here? This is done by the etching process. For the case of the semiconductor device, we also need a doping. This is done by the ion implantation and also by the diffusion. So now we will see that, for example, this is the metal nanostructures. You can see nanostructure or microstructure is the same. For instance, if we want to measure the electrical property of the carbon nanotube, you want to measure electrical property of the carbon nanotube. So what do you do? So you put the carbon nanotube below on the surface, then you put the metal electrode. You have the contact to measure the electrical property. So how to make those kind of metal nanostructures? If you do the cross section, side view, it is something like this. So metal on top of the substrate. So the main two methods is the direct etch process and the lift-off process. For the direct etch process, we have the thin film growth, we have the thin film deposition, etching, lithography. So first, deposition, deposit metal and resist. They will do the lithography to pattern the resist. They will etch away the metal using the polymer resist as etching mask. And finally, we can dissolve the resist. So we have the structure like what we have here. Another way is called the lift-off process. In this case, we deposit the resist first. Then we do the lithography to pattern the resist. Then we do the metal deposition. Then we do the dissolve the green color resist. So when this green color polymer is dissolved, so the metal on the top is gone. We leave behind the metal on the substrate. This is why it's called a lift-off process. So this is the general method of the pattern transfer. So as we just seen. So we have the resist, we do the lithography, we have the pattern. So afterwards, we can do the etching. This is like a direct etch process. We can do the etching, do the pattern transfer. We can also do the lift-off. So this is the lift-off process. In addition, we can also do the doping process. So we can use the resist as a mask for the doping, for the ion implantation doping. And another way we can do is to do the electroplating, to grow the metal from the bottom to the top. So those four processes, they are called a pattern transfer process. So now let's look at some history. Of the semiconductor technology. So first we look at Moore's law. So Moore's law said that the number of the transistors will be doubled every 2 years. The later it becomes every 2 years. The later it becomes every 3 years. And nowadays it is more than every 3 years. This is the Moore's law. I'm sure everybody have heard of the Moore's law. But there are two ways to double the number of the transistors on a chip. First is make the transistor smaller and smaller. This one is obvious. Secondly, we can also make the chip and the wafer bigger and bigger. But nowadays, the wafer size is 12 inch. Today, the wafer size is 12 inch wafer. So this is the scaling down over the time. You can see in the 1990s, every 2 years, we have a new node. After 2007, every 3 years, we have a new node. This is called a technology node. Node is called a half pitch. That means if we have the transistor, we have one transistor here, another transistor here, another transistor here. But we can see this is the gate. So this is the gate. So from here to here is the pitch. So half pitch. The half pitch means half the distance from here, from different transistors. So here, gate, G means gate. Gate for this transistor, gate for this transistor, and the gate for this transistor. So we can see, so in the 1998, 250 nanometer node, the 180, we go down smaller and smaller. So now look at what are the numbers, what is the meaning of the numbers. This one 250, this one 180. So what's the relationship between those two numbers? So they are related by a factor of 1 over square root of 2. If the pitch becomes 1 over square root of 2, then the area per transistor will become 1 over 2 because the area is proportional to the pitch square. So you can see 250 divided by 1 over square root of 2 becomes 180, then becomes 130. This number is half of this number. But this number is half of this number, and this number is half of this number. So every 2 nodes, the pitch becomes half. So then become 22 is half, or 45. But later on, you can see the number become deviate. This one is 18. In principle, this one should be 16. 32, 22, it should be 16. So today, if you read the newspaper, you know we're in a 5 nanometer. So today, for the microprocessor, we have the 5 nanometer node. But actually, the 5 nanometer node does not mean half pitch. Half pitch is not 5 nanometer. For the 5 nanometer node, the half pitch will be something 15 nanometer. But that means the definition of the node is no longer this rigid separation, because the companies, they want to make people happy. This is it becomes like a marketing term. So here it's called technology node, but from the recently it become marketing term. So people just say the numbers. For instance, the 10 nanometer node for Intel is equivalent to the 7 nanometer node for the TSMC. TSMC. The Taiwan Semiconductor Manufacturing Corporation, 7 nanometer is equivalent to Intel 10 nanometer node. So today, if you look at the node, they are no longer a half pitch. So it is possible to make the gate very, very small. In this case, it's 5 nanometer. But in reality, such a device will not work because the gate here cannot turn this off. There will be leakage. But today, 5 nanometer is not made by this way. Today, 5 nanometer is made by something called a FinFET. Fin. So fin is something like this. This is the fin. So we have the gate. The gate all around. This way, because the gate is all around, hold the fin, so it can turn off. The fin. So otherwise, if the gate is on the top, it cannot turn off the channel. So now let's look at the history of the device, of the transistors. In the 1940s, the R&D started. In the 1945, after the Second World War, the Biolab, they have a group of people, William Shockley, John Bardeen, and Walter Bratton. So this group, they want to develop a semiconductor replacement with the vacuum tube. 2 years later, they invented a transistor. They have invented the transistor. Now it's called transistor. So transistor was invented in 1947 by those 3 people, and they won the Nobel Prize in 1956. 1951, Shockley is the same as this Shockley, developed a junction transistor. This is more practical than the first transistor. And 1954, so the transistor is widely used for the telephone system. This is used as a switch. We know that for the telephone, we need to switch between different lines. So this is the 1947, the invention of the bipolar junction transistor. So those are 3 people, Shockley, Bratton, and Bardeen. They won the Nobel Prize in 1956. So this one, Bardeen, he won another Nobel Prize in 1971 or 1972 because he developed the theory for the superconductor. So this one, he won Nobel Prize twice. So this is how it looks for the first transistor. This is bipolar junction transistor. So we have emitter from here, collector from here. This is the base. They're pushed to the germanium base because it works, but this will does not look like very useful. So to make useful transistors, first is called junction transistor. It's done by the Gordon Hill and Morgan Sparks. You can see you grow the silicon wafer N NPN. You grow the silicon wafer, then you thin down the silicon wafer, then you dice it. Then you have the NPN. So NPN, this is the bipolar junction transistor. Then you have the aluminum wire, make the connection, and it will work. So here, aluminum wire is also connected to this side, but this is not a problem because of the very high contact resistance. This is called a junction transistor. This one is very successful. The next one is the alloy junction. Alloy junction in the 1950s. So what do? You have this N substrate. You put some indium. Then you anneal it. So the indium melts at 157 degrees, and this is p-type dopant. Because the indium is the same group as the boron. So indium is similar to boron. Boron is p-type. So indium is also a p-type. So you have the p-type. Then you have the PNP. You have this junction transistor. So this one is not very successful. This one is not very successful because the N has to be very thin. Otherwise, it will become 2 PN junction, NP junction. It will not work. But the base has to be very narrow or very thin. But if this is very thin, then it will be broken. It will be fragile. So this one is not commercially very successful. Next one is called a method transistor. So here the doping is done by this annealing process. So this is not efficient process for the doping. But this one, the doping is done by the epitaxial growth. Then there is the gas phase diffusion for the doping. For instance, we can use the phosphine gas to dope silicon with phosphorus to have this N-type silicon. You can see you start with N, then you do the doping, you do heavy doping, the top is converted to P, then you do even heavier, more heavy doping, the top is converted to N. So you have the NPN. You have this NPN, bipolar junction transistor. And then you put the electrode, then you isolate the silicon from here and here. Because this transistor needs to be isolated from the nearby transistors. We need isolation. If we isolate them away, then if there is another transistor, so this one will not be affected by this one because in the area in between is removed. But this causes a problem. So we have this called exposed junction. If there is some contaminant coming to here, then the performance will not be good. This is the problem. Then there is the invention of the IC, integrated circuit invention, in the 1959 by the Jack Kilby from Texas Instruments. So integrated circuit means we put many components in the same circuit. Here we have the resistors, capacitors, distributed capacitors, and transistors. We put everything in one chip. That in this case is the germanium chip. So this chip here has the function of the oscillator. So oscillator is because of the unstable positive feedback. But the main problem for this IC, you can see we have the gold wires. The gold wire floats on the free space, so you cannot make many devices because if you have so many wires, they will contact each other. So as you see here, this IC Kilby's inversion, this one, the main problem is the circuit element were connected with the gold wires. This gold wire is flow on the top of the wafer, so they are not, this is not good. So in the 1958, they have this something called a planar process. This is the big breakthrough. We use planar process. You can see planar. We no longer have the gold wires flow on the top. So how to make this wires connections? It is something like this. If this is the device, one here, this region here, one here. So you want to make a connection between, this can be the gate, this can be the gate. You want to make a connection between those two points. So what do you do? So first, you grow a silicon oxide layer. You grow a silicon dioxide. Layer. But this is a very good insulating material. You grow silicon oxide layer. Then you pattern and drill some holes You drill holes here and drill holes here. But the lithography and etching process, then you drill the holes. Then you have the holes. Your hole is etched. Then you do the evaporation of the metal layer, metal evaporation. And then the metal. So the metal will cover inside. You call it the metal layer. You can see the metal layer here. You see the metal layer here. Then finally, you can pattern the metal. You can pattern the metal layer by lithography and etching process. And in the end, those lines are connected to the transistors below the surface by through this hole. The material here is the silicon oxide. This is the planar process. So how to make the transistors by the planar process? It is done by this method. So this is how the transistor was made by the planar process. So first, we use gas phase diffusion. We use gas phase diffusion masked by the silicon oxide. So because silicon has this very good perfect oxide, that's why the technology shifted from the germanium to the silicon. The germanium does not have a good germanium oxide, but silicon has a very good silicon oxide that can be used for the diffusion. You can see here. So we grow a silicon oxide, then we do the lithography and etching to pattern it, then we do the boron diffusion. So boron, so this can be boron nitride or the boron. So we can use those gases as the boron source to diffuse. The boron becomes the p-type. Yeah, boron diffusion. Then with the oxidation, we grow another oxide. Then the boron also gets deeper through the oxidation process. Then we pattern it again by lithography and etching. Then we do a second phosphorus diffusion. So this can be can use the P. So we can use the pH3 gas to diffuse N-type. Then we have this NPN. So the main thing for this one is that you can see NPN. This junction here and this junction here, they're all below the surface. That means if there is some contamination on the surface, the devices will not be affected very much. So here is the planar process for the fabrication of the transistors and also for the fabrication of the metal connections. So this is the summary of the IC industry. So in the 1947, the three people from Bell Lab, they invented transistors. They won the Nobel Prize in 1956. 1958, Atala, he made the first MOSFET transistor. Then later on, Kilby from Texas Instruments and Noyce from the Fairchild, they invented the integrated circuit. They won the Nobel Prize in year 2000. Then 1959, John Herney, we have the planar process. This is very good technology, planar technology. And today we also use planar technology. In the 1963, we have the first CMOS circuit. In 1965, we have the Moore's law. Then there is the scaling rule and the roadmap. Here I wrote all those people here: Kilby, Noyce, John Herney, and everything is from Fairchild. Actually, this is very good story about Fairchild. So the people here see the Gordon Moore and Robert Noyce. They are all both from Fairchild, but they founded Intel. If you look at this website, you can see the history of the Fairchild and the Silicon Valley. So now I will go to this website. So this is about the Fairchild semiconductors. So this is the history about this one. In 1956, the Shockley who invented the transistor from Bell Lab. So he left Bell Lab to start a company called Shockley Semiconductor Laboratory in California. So he hired 8 people. He hired 8 young people. Nobody from Bell Lab wants to go to the West. So he hired 8 young people to the company. These 8 young people later become it's called the Traitors 8. But those 8 people is considered as the founder of the Silicon Valley. So you can see that those people, they founded Silicon Valley. You can see the names. So Gordon Moore and Robert Noyce, they are the founder of the Intel. This Sheldon Robert, John Gurney, and Jay Lars, they founded another company that later on became the Teledyne. Teledyne, is also a big company. They bought the Waterloo company and Delta. If you want to learn more about the history, you can read this. This is a kind of the history of the Silicon Valley. Okay, thank you.